Back to my class in analytic geometry. And for today's lesson, we will take up the midpoint between the endpoints of a line segment. But before that, for those who missed the first two lessons in analytic geometry, please search for my video. Art teaches analytic geometry lesson 1 and Art teaches analytic geometry lesson 2 on the distance between 2 points. To find the coordinates of the midpoint of a line segment, we take any two arbitrary points in the Cartesian plane. We let P1 with coordinates x1 and y1, and point P2 with coordinates x2 and y2 be the endpoints of the line segment. We do not know exactly the coordinates of the points P1 and P2, but we know that these points P1 and P2 are the endpoints of the line segment. And we will find the point halfway between the points P1 and P2. And we denote the point halfway between P1 and P2 as the point P with coordinates x and y. This point P is the midpoint, the point halfway between P1 and P2, the endpoints of the line segment. The line segment is denoted by this notation P1, P2, which means that the endpoints of the line segment are the points P1 and P2. And the coordinates of this midpoint are x and y. We will find the value of x, the abscissa of the midpoint. We will also find the value of y, the ordinate of the midpoint. And we will express these coordinates of the midpoint of the line segment with endpoints P1 and P2 in terms of the coordinates of P1 and P2. To simplify, we draw the points P1 and P2 in the first quadrant of the Cartesian plane. The Cartesian plane consists of the vertical axis, the horizontal axis, in which we write the abscissa, the first coordinate of a point, denoted by x. In the vertical axis, we write the ordinate of a point in the Cartesian plane. The vertical axis is denoted by y, so we call it the y-axis. At the intersection of the x-axis or the horizontal axis and the vertical axis or the y-axis is the origin, which we denote by point 0. And we take two arbitrary points in the first quadrant and we denote them by P1 and P2. Suppose this is the point P1 and this is the point P2. Now we draw the line segment that connects P1 and P2. The line segment with endpoints P1 and P2 is this line segment denoted by P1, P2. And we locate the midpoint of this line segment. We denote this by P, and we will find the coordinates of P. In particular, we will find the abscissa of P denoted by x and the ordinate of P denoted by y. If you project this point P1 down to the horizontal axis, you will locate the abscissa of P1. And it's denoted by x1. If you project this point P1 to the vertical axis, you will get the ordinate of P1 denoted by Y1. We do the same for the second endpoint of this line segment. Project P2 down to the horizontal axis to get the abscissa of the point P2, which is denoted by X2. And we project the point P2 to the vertical axis to get the ordinate of P2 denoted by Y2. We also do the same for the midpoint P. The midpoint P is halfway between P1 and P2. The point P must be exactly at the center, at the midpoint of P1 and P2. We project this point P down to the horizontal axis, and this will be the abscissa of the midpoint of the line segment, and we will find the value of X. We also project P to the vertical axis. The value of Y at this point is the ordinate of the midpoint, and we will also find the value of Y. We find the values of X and Y from the diagram. We now find the abscissa of the midpoint P. That is, we find the value of X. The midpoint P divides the distance between the endpoints of this line segment into two equal distances. The point P divides the distance between the points P1 and P2. The midpoint divides the distance between P1 and P2 into two equal distances. That is, the distance between P1 and P is equal to the distance between P and P2. The coordinates of P also divides the distance between the coordinates of P1 and P2 from the origin. We start with X. You can see that X is the abscissa of the midpoint P, and it is halfway between the abscissas of P2 and P1. That is, X, the abscissa of point P, is the midpoint of the abscissa of P1 and the abscissa X2 of P2. Which means that X divides the distance between X1 and X2. Or the distance between X1 and X2 is equal to the distance between X and X2. So we will get the distance between X1 and X, and the distance between X and X2. When you get the distance between 2 points in the x-axis, you always start with the point at the right. So to get the distance between X1 and X2, we start from X. The distance between X1 and X2 is equal to X minus X1. The distance between X1 and X2 is X minus X1. And this distance is equal to the distance between X and X2. The distance between X and X2 is given by X2 minus X. X2 minus X. And from this equation, we solve for X, the abscissa of the midpoint P, the midpoint of the line segment through P1 and P2. We transpose negative X to the left, and when you transpose, it will become positive X, and transpose negative X1 to the right, and when you transpose negative X1 to the right, it will become positive X1. From the left side, we have x. Transpose negative x to the left, we get plus x is equal to x2. Negative x1 to the right, it becomes positive x1. Or x plus x, addition of algebraic expressions. X plus x is 2x. And we rewrite this as x1 plus x2. x2 plus x1 is equal to x1 plus x2 because addition is commutative. That means in addition of real numbers or algebraic expressions, order is not important. Finally, to solve for the value of x, we divide both sides of this equation. Divide the left and the right side of the equation by 2 to make the coefficient of x equal to 1. 2 will cancel out from the left side. You get x equals x1 plus x2. Divide by 2. This is the abscissa of the midpoint of the line segment through points P1 and P2. The abscissa x of the midpoint P is equal to the sum of the abscissas of the endpoints of the line segment divided by 2. We will do the same process to find the value of the ordinate of the midpoint P. We find the value of y using the same process we use when we find the value of x, the abscissa of the midpoint. Now we find the ordinate of the midpoint of the line segment through the points P1 and P2. The ordinate of the midpoint also divides the distance between the ordinates of the endpoints of the line segment. That is, the value of y here is halfway between the values of y1 and y2, which means that the distance between y1 and y is equal to the distance between y and y2. When you get the distance between 2 points on the vertical axis, you start with the higher point. We get the distance between y1 and y2, and that distance is given by y minus y1. We write y minus y1 is the distance between y1 and y. And this distance is equal to the distance between y and y2. Again, when you get the distance between 2 points on the vertical axis, you start with the higher point. Hence, the distance between y and y2 is given by y2 minus y. And this distance y2 minus y is equal to the distance between y and y given by y minus y1. From this equation, we solve for y, the value of the ordinate of the midpoint P. This negative y we transpose to the left side because all the terms containing the unknown variable y must be at one side of the equation. We transpose negative y to the left side and it becomes positive y. And negative y1 we transpose to the right. And when you transpose negative y1 to the right side of the equation, it becomes positive y1. From the left, we have y negative y to the left, it becomes positive y equals y2, and we transpose negative y1 to the right, we get positive y1. By addition of algebraic expressions, y plus y, the coefficient here is understood 1, and the coefficient of y in the second term is also understood to be 1. So 1y plus 1y equals 2y. And y2 plus y1, we transpose negative y1 to the right, it's positive y1. And y2 plus y1 by commutative property is the same as y1 plus y2. And we divide both sides of the equation by 2 so that we get y only at the left side, and y will cancel out from the left side. We have y equals y1 plus y2 equals 2. Divide by 2. This is the ordinate, the value of the ordinate y of the midpoint of the line segment through the points P1 and P2. The ordinate of the midpoint P of the line segment through P1 and P2 is equal to the sum of the ordinates of the points P1 and P2 divided by 2. So we now write the coordinates of the point P. Therefore, the midpoint P, halfway between the points P1 and P2, has coordinates. The abscissa is given by the sum of the abscissas of the endpoints of the line segment divided by 2. And the ordinate y of the midpoint is given by the sum of the ordinates of the endpoints of the line segment divided by 2. These are the coordinates of point P, halfway between P1 and P2. Because the midpoint is exactly at the center, at the middle, between P1 and P2, we said earlier that point P divides the distance between P1 and P2 into two equal distances. Hence, the distance from P1 to P2 is equal to the distance from P to P2. And if you add this distance P1 to P plus the distance from P to P2, the sum must be the distance between P1 and P2. And we will now check that using the coordinates of the midpoint P. We recall the given and the coordinates of the point that we have derived. The given is the line segment with endpoints P1 and P2. And these points P1 and P2 are arbitrary points in the Cartesian plane. So they can be any points in the Cartesian plane. But to simplify our derivation of the coordinates of the midpoint P, we plot P1 and P2 in the first quadrant. The coordinates of P1 are x1 and y1. The coordinates of P2 are x2 and y2. And we have derived earlier that the coordinates of P, the abscissa is equal to x1 plus x2 divided by 2. And the ordinate of the midpoint is given by y1 plus y2. The ordinates of P1 and P2 added together, and the sum is divided by 2. Because P is halfway between P1 and P2, we say that P divides the distance between P1 and P2 into two equal distances. That is, the distance from P1 to P is equal to the distance from P to P2. And we will now show that the sum of the distance from P1 to P plus the distance from P to P2 is equal to the distance between the endpoints P1 and P2 of the line segment. Again, to simplify our solution, we take the square of both sides. We raise the left side and the right side of the equation to the power 2. From the left, we have P1P plus P2 square equals to the square of the distance between P1 and P2. For the left-hand side, we apply one of the product rules from algebra for the square of a sum. That special product rule says that the square of a sum is equal to the square of the first term, the square of the distance between P1 and P, plus twice the product of the two terms, twice the distance between P1 and P, twice the product of the distance between P1 and P, and the distance from P to P2. And the last term in the square of a sum is the square of the second term, the square of the distance from P to P2. And this is equal to the square of the, it should be equal to the square of the distance between the endpoints of the line segment. We start from the right side. You may start from the left side. From the right side, we have the square of the distance between P1 and P2, the endpoints of the line segment, and the square of the distance between P1 and P2 by the distance formula is equal to the square of the difference of the abscissas of these endpoints. Difference of the abscissas x2 and x1. And square it. Plus the square of the difference of the ordinates of P1 and P2 plus the square of the difference of the ordinates y2 and y1. y2 minus y1. This is the distance, the square of the distance between the points P1 and P2, the endpoints of the line segment. It is equal to the sum of the square of the difference of the abscissas of the endpoints and the square of the difference of the ordinates of the endpoints of the line segment. And we will show that when we simplify the left-hand side of this equation, which we obtain by getting the square of the sum of these two distances, after simplifying, we should get this sum or the square of the distance between P1 and P2. That is, we will show that the value of this sum is equal to the value of the distance between P1 and P2. And we have started out from the right-hand side, and we get this value of the square of the distance between P1 and P2. Now we will find the value of the left hand side, and we will show that after we simplify it, we will get this value of the square of the distance between P1 and P2. We start with the square of P1 and P2, the square of the distance between P1 and P2. We write the square of the distance between P1 and P. This is P1 and P, and we write the square of the distance between these 2 points, one endpoint of the line segment and the midpoint of the line segment. And the square of the distance between 2 points is equal to the square of the difference of the abscissas of P and P1. We start with the higher point P, x1 plus x2 divided by 2 minus the abscissa of P1, x1. We write x1 plus x2 all over 2 minus x1. And we take the square of it plus the square of the difference of the ordinates of P and P1, y1 plus y2 all over 2 minus y1 squared. We write open parenthesis y1 plus y2 all over 2 minus y1 squared. And we simplify the right hand side. The square of the distance between P1 and P equals the denominator of x1 is 1, and we get the LCD, lowest common denominator, between 2 and 1, and the LCD is 2. We find the numerator. 2 divided by 2 is 1, multiplied by the numerator x1 plus x2. x1 plus x2. Again, the denominator of x1 is 1. 2 divided by 1 is 2. Multiplied by negative x1, you get negative 2x1. And square. Plus, for the second term, the denominator of y1 is 1. And the LCD between the LCD of 2 and 1 is 2. And we find the numerator LCD 2 divided by the denominator 2 of the first term is 1, multiplied by the numerator y1 plus y2. Denominator of y1 is 1, 2 divided by denominator of y1, 1. 2 divided by 1 is 2, multiplied by negative y1 minus 2y1 squared. We simplify further by combining like terms in the numerators. We get the square of the distance between P1 and P is equal to, we start with x2, x1 minus 2x1. These are like terms. The common literal coefficient is x1. So we add the numerical coefficients, 1 plus negative 2. Or 1 minus 2 is negative. Copy the common literal coefficient x1. Denominator is 2 to the power 2. Plus, simplify the numerator, add the like terms y1 and negative 2y1. We write first y2 because y2 is positive. y2 Numerical coefficient of y1 is 1. Minus 2 is negative 1. Minus, copy the common literal coefficient y1 over the denominator 2 square. So this is the value of the square of the distance between P1 and P2. And we also need that in the second term. Next, we find the square of the distance between P and P2. And after we get that, we substitute the values of the square of the distance between P1 and P2, the square of the distance between P and P2, the distance between P1 and P2, and the distance between P and P2, and we will simplify, and we should get this one. The square of the distance between the endpoints of the line segment P1 and P2. Now we will get the square of the distance between the midpoint P and the second endpoint of the line segment. The square of the distance between P and P2. And we will obtain that by using the distance formula. We have the square of the distance between P and P2 by distance formula is equal to the square of the difference of the abscissas of P2 and P. Abscissa, we start with the higher point P2, x2 minus x1 plus x2 all over 2. We write x2 minus x1 plus x2 over 2 to the power 2. This is actually negative of x1 plus x2. So when you take the negative of x1 plus x2, you multiply x1 and x2 by negative. Plus the square of the difference of the ordinates of P and P2. Ordinates of P2 and P, y2 minus y1 plus y2 all over 2 square. We have y2 minus y1 plus y2 all over 2 square. And we simplify each term at the right hand side. We have the square of the distance between P and P2 equals, the denominator of x2 is 1. So the LCD of 2 and 1 is 2. 2 divided by denominator of x2, 1 is 2. 2 divided by 1 is 2. Multiply by x2. We have 2x2. And 2 divided by denominator of the second term is 2 is 1 times negative. Negative 1 multiplied by x1 plus x2. It's actually negative times x1 plus x2. Square plus denominator of y2 is 1, hence the LCD of 2 and 1 is 2. And we find the numerator, LCD 2 divided by denominator of x2 is 1. 2 divided by 1 is 2 multiplied by y2, 2y2. LCD 2 divided by the denominator of the second term is 2, 1. 2 divided by 2 is 1, multiplied by negative, negative 1. multiply by the sum y1 plus y2 square. And we simplify each term we simplify the numerator of each term. And by distributing -1 from outside and then combining like terms in the numerator, we have the square of the distance between P and P2 equals numerator 2x2 distribute -1 multiplied by x1 -x1 negative multiplied by positive -x2 to the power 2, denominator is 2, plus 2y2 distribute negative to the sum, negative times positive y1 is negative y1, negative multiplied by positive y2, negative y2 is square, and all over 2. Now we combine like terms in the numerators of these terms. We have the square of the distance between P and P2 is equal to, the like terms are 2x2 and minus x2. You add the numerical coefficient. The numerical coefficient of the x2 in the last term is -1. 2 minus 1 is 1. Multiplied by x2 is x2. Again, 2x2 minus x2 is x2 minus x1 all over 2 square, plus the like terms in this term in the numerator are 2y2 and negative y2. Again, you add the numerical coefficients to minus 1 here. 2 minus 1 is 1 multiplied by the common literal coefficient y2 minus y1 all over 2 to the power 2. So this is the value of the square of the distance between P and P2. You can see that it is the same as the square of the distance between P1 and P2. And we will now substitute the square of the distance between P1 and P, which we have shown is equal to this. We substitute the distance between P1 and P, which is given to this, obtained from here the square of the distance between P1 and P by getting the root of both sides. We substitute the value of the distance between P and P2, which we can get from here by getting the root of both sides. And we finally substitute the square of the distance between P and P2, which is given by this. And after substitution, we will simplify. And we will show that after simplifying, it is equal to the square of the distance between P1 and P2, which is given by this. This is the square of the distance between P1 and P2.
Ikakasal ka na ba? Tinig ko'y kakasal ka. na, panakibutas na lamang ako. Girl, hindi kita masisi, alam kong pangarap mo yan. Girl, hindi kita masisi, kailangan mo ring matikman ang sarap nito. Buhay na kung mahal mo siya, sige papasal ka, sige pagpatuloy mo na, panakibutas na lamang, panakibutas na lamang ako.
We now substitute the values we obtained for the square of the distance between P1 and P, which is given by this, the square of the distance between P1 and P. We substitute the value of the distance between P1 and P given by this, and the distance between the midpoint and the second endpoint of the line segment given by this, and the square of the distance between the midpoint P and the second endpoint of the line segment, which is given by this. But before we do that, I would like to simplify the second term. I will get first the product of the product of 2, the distance between P1 and P, and the distance between P and P2, and we will substitute the value that we will obtain to the second term. So we start with the second term. The product of 2, the distance between P1 and P, times the distance between P and P2, equals to the distance between P1 and P is given by the square root of the square of x2 minus x1 all over 2 plus the square of y2 minus y1 all over 2. We write 2 times the square root of x2 minus x1 over 2 squared plus the square of y2 minus y1 over 2 squared multiplied by the distance between P and P2 given by this, which is the same as the distance between P1 and P. So the distance between P and P2 is also equal to the square root of x2 minus x1 all over 2 square plus y2 minus y1 all over 2 square. To simplify the right hand side, we apply the property of radicals that says the product of x and the product of the root of x and the root of x is equal to x. we apply this property to the right hand side, you can see that the x in this property is equal to the sum of these squares. And this is the radicand of this radical expression. The radicands of these two radicals are the same, and they are the x in this property. So the product of these two radicals simplifies to x, which is the radicand. We have 2 times the distance of P1 and P times the distance between P and P2 is now equal to 2 times the square of x2 minus x1 all over 2 square plus the square of y2 minus y1 all over 2 to the power 2. And we simplify, apply the property of exponent. The square of this quotient is equal to the square of the numerator divided by the square of the denominator. So we have 2 times the square of the numerator, x2 minus x1 square divided by the square of 2, 4. This is 2 times the radical. Because we have 2 times the product of this radical and this radical equals 2 times the product of this radical expression and this radical expression is simply the radical. By this property, the root of x times the root of x simplifies to x. And x is this radical. So this simplifies to 2 times the radical. And we are now simplifying this. We have 2 times the square of x2 minus x1 divided by square of 2, 4 plus square of y2 minus y1 divided by the square of 2, 4. You can see in this factor the 1/4 is a common factor. If you factor out 1/4 and you multiply by 2, you will get 1/2. So this is equal to factor out 1/4, 1/4 from this factor. We have 2 times 1/4 times x2 minus x1 square plus the square of y2 minus y1. y2 minus y1 square. And 2 times 1/4 is 1/2. So multiplying 2 by 1/4, we get the product of 2 times the distance between P1 and P and the distance between P and P2 is equal to 1/2 of the sum of the square of x2 minus x1 and the square of y2 minus y1. We now substitute these values into this equation, which is the expansion of the square of this binomial. The square of the sum of the distance between P1 and P and the distance between P and P2. The square of the distance between P1 and P is given by this the square of x2 minus x1 1 over 2 square plus the square of y2 minus y1 over 2. The square of y2 minus y1 over 2 plus twice the product of the distance between P1 and P2 and the distance between P and P2 we have shown is equal to 1/2 plus 1/2 of the sum of the squares of x2 minus x1 and y2 minus y1. 1/2 times the square of x2 minus x1 plus y2 minus y1. And the last term is the square of the distance between P and P2, which is given by this, the square of the distance between P and P2 is given by x2 minus x1 over 2 square plus the square of y2 minus y1 over 2. The square of y2 minus y1 over 2. And we will simplify the left side of this equation. We simplify each term from the right hand side of the equation. We start with these terms by applying the property of exponent. The square of this quotient is equal to the square of the numerator divided by the square of 2. We write the square of x2 minus x1 over 2 is equal to the square of x2 minus x1. Divide by the square of 2. Divide by the square of 2 is 4. Plus the square of this quantity equals the square of the numerator y2 minus y1 squared divided by the square of 2, 4 plus this term. This term cannot be simplified any further, so we write this as is plus 1/2. 1/2 times the square of x2 minus x1 plus the square of y2 minus y1 plus the last two terms, which can be simplified by applying the property of exponent. The square of this quotient equals the square of the numerator divided by the square of the denominator. So this term is equal to the square plus the square of x2 minus x1 divided by the square of 2. Divided by the square of 2 is 4. Plus the square of this quotient is equal to the square of the numerator divided by the square of 2. So this last term is equal to a square of y2 minus y1 divided by the square of 2, 4. Now we simplify further by combining like terms. This term and this term are like terms. They both have the same literal coefficient. Common literal coefficient is the square of x2 minus x1. Square of x2 minus x1. Thus, we add the numerical coefficients. 1/4 plus 1/4 is 1/2. 1/2 times the common literal coefficient is square of x2 minus x1. Square of x2 minus x1. And we combine these two terms. They are similar terms. Their common literal coefficient is the square of y2 minus y1. Square of y2 minus y1 is the common literal coefficient. Thus, we add their numerical coefficients. 1/4 plus 1/4 here is 1/2. Times the common literal coefficient, the square of y2 minus y1. Plus, here you may distribute 1/2 to each of this term by distributive property of multiplication over addition. We distribute 1/2 plus 1/2 times x2 minus x1 square plus 1/2 times y2 minus y1 square. And this expression can still be simplified by combining like terms. This term and the third term are similar terms. Their common literal coefficient is the square of x2 minus x1. Square of x2 minus x1. Thus, we add their numerical coefficients. 1/2 here plus 1/2 here is 1. Times their common literal coefficient is square of x2 minus x1 is equal to x2 minus x1 squared. The second term and the last term are also similar terms. Their common literal coefficient is the square of y2 minus y1. Square of y2 minus y1. So we add their numerical coefficients. 1/2 here plus 1/2 here. 1/2 plus 1/2 is 1 times their common literal coefficient. The square of y2 minus y1 is the square of y2 minus y1. But this sum, the square of x2 minus x1 and the square of y2 minus y1 is exactly equal to the square of the distance between P1 and P2. We have shown that if we substitute the values of the square of the distance between P1 and P, the distance between P1 and P, the distance between P and P2, and the square of the distance between P and P2, and we simplify it, we simply get the sum of the square of x2 minus x1 and the square of y2 minus y1, which we have shown earlier is equal to the square of the distance between P1 and P2. Thus, this expression is, we have shown, is equal to the square of the distance between P1 and P2. And the left-hand side is a perfect trinomial which can be written as the square of a binomial with terms P1, the distance between P and P, P1, the distance between P1 and P, plus the distance between P and P2. The square of this binomial is given by this, or this perfect trinomial is equal to the square of this binomial. And this is equal to the square of the distance between the endpoints of the line segment. If we extract the root of both sides, we get the distance between P1 and P plus the distance between P and P2 is equal to the distance between P1 and P2, or the endpoints of the line segment. Sorry, this is P1 and P2. Thus, we have shown that if point P is the midpoint of the line segment with endpoints P1 and P2, the midpoint divides the distance between the endpoints of the line segment into two equal distances, and the sum of these distances P1P and the distance P2 is equal to the distance between the endpoints P1 and P2 of the line segment. So, for our next lesson, we will take some examples for obtaining the midpoint of line segments whose endpoints are known. If you have question for today's lesson, you post your question in the comments below, but don't forget to subscribe to my YouTube channel, Art Kalisan, and I will see you in the next lesson. Thank you.